had enjoyed the conference dinner and the show on the boat last night. So it's time to get back to the scientific program again. So our first speaker will be Andrea Mari from NES in Italy, and he will going to talk about majorization and entropy at the output of bosonic Gaussian channel. Let's welcome him.
So thank you for the introduction, and thanks to the organizers for giving me this opportunity of presenting this talk. So this talk, can you hear me? Yes. This talk is divided in two parts. In the first part, I will try to give an overview of all the recent results about the entropy at the output of bosonic Gaussian channels. And these results were obtained by the authors that you see here. So Vittorio Giovannetti, Alexander Holevo, Raul Garcia-Patron, and Cerf. And in the second part of the talk, I will focus mainly on the proof of a result where I was involved together with Vittorio Giovannetti and Holevo, which is the proof of the so-called majorization conjecture. And later I will tell you what it's about. Here, okay. So this is the outline. So the proof, as you will see, is very simple. So there will be a long introduction to give this general overview, as I said, but also to introduce some tools in such a way that even if you are not an expert of Gaussian channels, you can understand, I think, the basic idea of the proof. So let's start with what is the general question behind this talk, okay? So I have to apologize that this has something to do with the real world, even if this conference is quite unusual, but we are talking about realistic channels devices, like assume that you have an input radiation mode, like optics or microwaves or whatever, and then you transmit via some medium that usually is well described by a Gaussian channel, and then you care about what is the noise at the output. And the general question is the following one. What is the minimum noise that we can achieve? So in a better way, what are the input states that minimize the noise at the output? And this, of course, is a very important implication in communication theory, because if we know what are the states that are less affected by the noise, we can use such states as a code words, optimal code words for transmitting information, and then we can use it to determine the capacity of the channel. And but before trying to answering this question, we should clarify in a more rigorous way what we mean with disorder, in which sense one state is more disordered than another one. And in information theory, there are two main ways of saying that one state is more disordered than another one. One is the usual phenomenon entropy. So if rho 1 is more disordered, it means that its entropy is larger. Okay, that's the usual one. But there is a stronger way of saying that one state is more disordered, which is the majorization relation. I remind you that the definition of it. So you just take the eigenvalues of the density operators, you order them in a decreasing order, and then you sum the first k largest eigenvalues, and you check if this inequality is satisfied. Okay, that's the definition, and in a way it measures how much one distribution is more peaked than another one, more confined. And this condition can be shown that it's equivalent to the following theorem that says that if rho 2 majorizes rho 1, then for every concave function you have that the trace of the function of the operator satisfy this inequality. So if a state is pure according to this definition, it minimizes concave functions. And in particular, since the entropy is a concave function, you have that this relation implies that also the entropy, this criterion implies also the entropy criterion, okay? And according to these two definitions of disorders, two conjectures were proposed some time ago about the entropy at the output of a Gaussian channel. So the general idea is that coherent states they were supposed to be the input states that produce the minimum amount of noise at the output of the channel. And actually, the conjecture was that the minimum output entropy is minimized by coherent input states. This was a weak conjecture, if you want, but there was also a stronger conjecture, which is that the output corresponding to coherent input states majorizes every possible output state. Okay, that's the output state of a coherent state. This will majorize every other output state. And in this talk, I will give a proof of this, which also implies, for the reason that I shown before, also the other one. But to understand why people care about this problem, it's good to give a more general overview of so why these conjectures were proposed and what are the implications. So let's see some general connection between several open problems that now are not more open, let's say. So this was indeed the situation before December of 2013. And as you can see, as I said you, the majorization conjecture implies the minimum output entropy. But these were introduced exactly for the task of computing the classical capacity of a Gaussian channel. So if one could show this or this one, then you immediately have a closed formula for the classical capacity of a Gaussian channel. And since for many times it was hard to prove this conjecture, it was proposed an alternative approach. Let's try not to solve this, but try to, let's say, generalize to the quantum setting a classical result, which is the so-called entropy power inequality. So in classical information theory, this is a very powerful and important result. It's about, again, optimality of Gaussian, let's say, random variables for minimizing the entropy again. And you can generalize this entropy inequality in two ways in the quantum setting. One is the entropy photon number inequality, and one is the entropy power inequality. So this is stronger than this, and this is still an open problem, and this was shown by Koenig and Smith in a particular case of a 50-50 beam splitter, let's say. And why these are important? Because, for example, this conjecture would imply the classical capacity, and while this other one is a little bit weaker, but it gives very good bound for the classical capacity or for many other optimization problems. So when it's gray, it means that it was an open problem. When it's like in this color, it means that it was solved for some specific cases. So on this other part, we have some implications about related to the majorization. So it was conjectured that a majorization relation was present also in the phase space for optical systems. What does it mean? That you can associate a positive distribution to a quantum state, which is not a real distribution as you have in classical physics. You can ask if this Q function of a coherent state majorizes every other possible Q function. This was an open problem that was solved in a different context by Lieb and Solovey very recently. And I will show you that this is also related to this conjecture. And also, you can ask if not just the entropy, but also every Rayleigh entropy is minimized by coherent states. And this has been recently used to prove a strong converse theorem for the classical capacity. So what does it mean, a converse theorem? It means that the classical capacity tells you the maximum rate at which you can use the channel to transmit information at zero error. The converse tells you that if you try to use the channel at a larger rate, then the error will asymptotically go to 1. So it's impossible. There is a sharp transition. And okay, this was the situation, as I said, like 1 year ago, let's say. And then this guy came and put a bomb in the middle of this open field. And the bomb was the solution of the central conjecture, so the minimum output entropy conjecture. So this was a work by Giovannetti, Holevo, and Garcia-Patron. So I can say that this is a very good work because I'm not an author of this, so I can advertise it. And it's a very good work, not just because it solves the conjecture, but as you will say, it's really like a bomb because it contains a trick that it has been useful for solving many other problems. Because as you can see, this is December 2013, and then like 4 days after the majorization was solved, and then the classical capacity was explicitly computed, the strong converse theorem was obtained, the entropy power inequality was proven for every phase-insensitive Gaussian channel, and the phase-space majorization was also proven. The only open problem, which is still open, is the entropy photon number inequality. But this is why I say that this was really a breakthrough. And actually what I'm talking about is not this paper, but this one now, the proof. I will give the proof of this. But I have to say that 90% of the proof is similar to this, to the proof of the central conjecture. So this is the state of the art. Now, this can be a little bit boring if you know Gaussian states, but I think here the audience is very different, so I will give you the tools to understand the proof. So we are talking about bosonic Gaussian systems, so infinite dimensional Hilbert space. The Hamiltonian is, if you want, the one of the harmonic oscillators, and then you have the basis given by all the eigenstates. That's called the Fock space. But there is also another important basis in this space, which is given by the coherent states. This is, if you want, a little more physical. They are easier to realize experimentally. These states can be defined in many ways. They are the eigenstates of the annihilation operators, or you can see as the vacuum state that you displace in phase space. So the minimum uncertainty state displaced around in phase space, and the displacement operator is just a linear evolution with an Hamiltonian which is linear in A and A dagger. So this operator is very important because you can use it as a basis for expressing a bosonic state. And you can define, for example, a characteristic function, which is something like a Fourier transform of a state. It's a quantum Fourier transform. So this function contains all the information about the state. And it's very useful to use when you talk about Gaussian states and Gaussian channels. So the Fourier transform is the so-called Wigner functions, which is something like a probability distribution in phase space, but it can get negative values. Another quasi-distribution is the so-called Husimi function or Q function. This is positive by definition, because it's just the projection of rho on the set of coherent states. It's like the result of a measurement, if you want, the probability of a measurement. And then one can use this function, as I said before, to define entropy and majorization in phase space using classical definitions of entropy and majorization. So this is different from the entropy of a state, of course. What are Gaussian states? Gaussian states are states where these functions are Gaussian. I'll give you just 3 states that we will use later: the vacuum, the coherent state, and the thermal state. So these are the functions. As you can see, the vacuum has the minimum noise. It's a Gaussian with the minimum noise allowed by the Heisenberg principle. Also the coherent states, while thermal states have a noise which is proportional to the number to the temperature, to the number of photons. What are Gaussian operations then? What is a channel? Gaussian channel is a completely positive trace-preserving map that maps Gaussian states into Gaussian states. So if it is unitary, it is generated by a quadratic polynomial in A dagger. In general, you can write with the usual dilation of a channel with a unitary acting in a larger Hilbert space, where now the ancillar and the unitary are both Gaussian. These are all the Gaussian channels. So the Gaussian channels that we care about are phase insensitive, because the result will be valid for this. And they are defined in this way formally, so they are invariant with respect to phase space rotations. At the level of characteristic functions, it means that they are defined by two parameters for one mode, the amplification parameter and the noise parameter. Almost the most important channels are in this class. Let's see a little bit what are these channels. So we have the quantum limited attenuator, which is basically physically a beam splitter, where you send your state through the beam splitter, you couple it with the vacuum. And then the definition of the channel formally is just this one, where the unitary acts in the following. It's the beam splitter unitary, basically. You amplify, you attenuate your signal, and then you mix it with the operator of the vacuum. What is the thermal attenuator instead? It's the same, where here you put the thermal state as an ancillary state, okay? Then we have also the equivalent, but in the opposite direction, which is the amplifier. This time you amplify your signal because you map A to Ka, where K is larger than 1. But formally it's the same. Again, you couple your system with the vacuum, and you trace out one part of the system, and that's the output. The thermal amplifier, again, is the same, where the ancillary is the thermal state. An important channel that we will use later in the proof is the complementary of the quantum amplifier, which is defined in the usual way in which you define the complementary channel. So instead of tracing out the path, you trace out the system. So you can always define the complementary channel. And in the case of an amplifier, the channel acts in the following way. You multiply your signal, let's say, with a factor of square root of k minus 1, but you also change A into A dagger. This is why it's called phase conjugation in optics. And this is not phase covariant, but it is phase contravariant. And it will be important later. And the important aspect that we will use later is the fact that if you send a pure input state, this is valid for every complementary channel. If you send a pure input state, the spectrum of the output of the main channel is equal to the spectrum of the complementary, just because the global pure state is pure. Then the reduced state have the same spectrum. So each time you see a square, it's something that we will use later in the proof. So this will come out later. So finally, we have also the additive noise channel, where you don't amplify, you don't attenuate the system, but you just displace it randomly in a Gaussian way. You just add Gaussian noise. And an important operation, which is actually not a channel, it's not completely positive, but it's important later, you will see, it's the transposition operation, which is just defined as you take your state in the Fock basin, you take the transpose. Again, of course, this doesn't change the spectrum of the state. This is a summary of the channel with all the effects defined in the characteristic function. And as you can see, they are basically defined by two parameters, one here and one here. And then it makes sense to find a canonical decomposition of these channels. There are many decompositions, but the one that we are going to use is the following one. So every phase-insensitive Gaussian channel is equivalent to a quantum limited attenuator, a beam splitter, composed with an amplifier. All of the channels that we have seen before can be decomposed in this way. And if it is phase contravariant, like the complementary of the amplifier, then you have the same decomposition, but you have to add the transposition at the end. That's very simple. You can just show this decomposition by the definition of the channel, basically. And for example, this is the complementary of the amplifier. You get that it has this decomposition with a particular value of the transmissivity of the beam splitter. This is the key part, actually, of the proof. You will see later, one of the key parts. So actually, an important ingredient that we need for the proof is a very old result. So it came out at the beginning of quantum optics, if you want. which is about the entropy at the output of a beam splitter, of a quantum limited beam splitter. So the first proof of the result is very old. It's 1966 by Aronov, and it came out in a context which is completely different. It seems completely different. So the task here is to characterize classical radiation with respect to quantum radiation. And they ask the following question. So assume that you have a radio transmission of some signal, and then this the signal is divided into outputs, B and C. And this is the case 1. In the case 2, you have a similar situation, but you have two independent radio transmission of the same, let's say, they say the same violin concert. They really write this in the paper. So the same violin concert, they suppose they have the same recording, they are identical. So you have exactly two independent systems making the same experiment, if you want. And the question is it possible to distinguish between case 1 and case 2? So from a receiver point of view. And the result that they show is the following, that it is always possible unless the signal is modulated in the basis of coherent state. So basically, if you use a classical radiation, then it is impossible. But if you use every other quantum radiation, that it is always possible. So how this is related to our problem? This is related because when it is assume that the output of this beam splitter is entangled, okay, then it is always possible to distinguish between this case, because this is a product state, this is an entangled state. You can discriminate. But if the output is a product state, then it is indistinguishable. And then this gives indirectly a proof that the only way to get a pure output state at a beam splitter is to send a coherent state at the input. So let's write this more clearly. So this is the golden property, because it will be very powerful later. The only input states producing pure output states for a quantum limited attenuator are coherent states. So if you want, the proof is very simple, but I think I don't have time to explain everything. Just write the definition that you get a product state at the output in terms of the characteristic functions, and then you will see that the only solution are coherent states. That's just, you can do it in phase space. So remember, this is a golden property that we will use later. So finally, we can go to the proof. This is what we have to show. For every input state here, coherent states always majorize the output state. Actually, the best way to prove this is to show something similar to this equivalence theorem in majorization theory. So we prove that for every concave function, actually every strictly concave functional, and for every quantum state, the functional is minimized by coherent input states, actually only by them. This is a little bit stronger than the majorization, because you also have this only if part. I remind you what we mean with strict concavity, just concavity, but the inequality is strict unless ρ1 is equal to ρ2. So let's try to prove this. So we know that F is unitary invariant and strictly concave. So if we look at this minimization problem without the channel, just apply to every state, it is clear that it is optimized by pure state, and every state, pure state, is good because it is unitary invariant, so every state is good. So if we have a quantum channel where the output is pure, we already solved the problem, because that's the optimal state. And this is a special case, exactly the quantum limited attenuator. We apply the golden property, and we know that the only way to get a pure output is if and only if the input is coherent. So in this case, we already have the proof. So in the general case, we apply the previous decomposition. So we know that every phase insensitive channel can be written as a beam splitter and followed by an amplifier. And this tells us that it is enough to prove the theorem only for the quantum amplifier. So if we show that the coherent input is optimal for the amplifier, then it is optimal also for this channel, because the beam splitter maps coherent states into coherent states. So we reduce the whole proof to the case of the amplifier. And then again, we use the strict concavity of the function. And we know that it is minimized only by pure input states for all invertible channels. Why we need this hypothesis? Because if you have a channel that whatever input you put, it gives you, let's say, always the vacuum, then this is like a pathological channel, and it's not even it's not more true, this fact. Okay, you can put every input, you always have an optimal state. So the only way, but all the channels that we are talking about are invertible in the sense that they different inputs give different outputs. Then we have this optimality. We know that the input must be pure. So then let's apply this. So let's consider this quantum limited amplifier and send a general pure input state. So we know that since it is quantum limited, its output and the complementary will have the same spectrum, which means that the function will be the same, because the function will be a function only of the spectrum, because it is unitary and invariant. Now we have this. We know that this can be decomposed again according to the decomposition theorem. So this will be equal to a beam splitter, an amplifier, and a transposition. We just put this substitution here. And we know that the transposition doesn't change the spectrum, so we can neglect it. We have amplifier, and beam splitter. And actually, up to this point, this is the same proof of this paper that I told you before. The only difference is that instead of using entropy, we use a strictly concave function. And now we will apply the golden property, because what we know is that let's take a general input state psi and assume that this is optimal. So this will minimize this function. Then, because of this, also the output of the beam splitter must be an optimal state. But we know that optimal state, because of strict concavity, they need to be pure. Then the only way for this state to be optimal is that when subject to the beam splitter, to the attenuator channel, the output is pure again. And we know exactly because of this very old result of quantum optics, that this is possible if and only if psi is a coherent state. So we have, so we prove the theorem, and we also have the only if part. So what does it mean? That the pure state, coherent state, minimize every strictly concave output functional of the state. Moreover, the equality is obtained only if rho is coherent. And as I said before, this is basically the same definition of majorization. There is only a little problem because of this hypothesis of strict concavity. Usually, the equivalence is between concave, functional, and majorization. Strict concavity, usually you don't find it in the literature, but it can be easily shown that it's not a problem. And so this is the result. What about the implications that I said you before? Why this implies many other problems? Well, because you have to take the right function and you get a lot of results. So if you take the entropy, this is a strictly concave function, not just concave, but strictly concave. Then you get a strong version of the minimum output entropy. So the output entropy is minimized only by coherent input states. Also, you get the equivalent result for every Rényi entropies of order p larger than 1. Why? Because you just take, again, 1 minus the trace of rho to the p. This is positive and strictly concave, so you get immediately the result. And you also add the phase space majorization result. This is a bit more complicated, and you can find the proof in this paper here. So to conclude, this was the original question. So what are the input states that minimize the disorder at the output of the channel? And now we can say that coherent states are optimal for every kind of disorder measure that you can imagine, because basically majorization is very powerful in the sense that if you use Renyi entropy, or other functionals, you get the same result. So this is the map again of all these open problems with all the references. I just want to say that there are still gray squares here. One is the entropy photon number inequality that I told you before. One is the quantum capacity, which is still open for Gaussian channels. So thank you, that's all. I think I was a bit too fast.
Yes.
So if you want, I have how much time?
We have 20 minutes.
Okay, good. Then I would like to give you this proof, okay? Because I was very fast when I say that the minimization of strictly concave functional implies majorization. It is a bit well known, but it's good to give the proof. It's very simple. So this is the statement. For every non-negative strictly concave function f of x, now we are talking about vectors. We don't care about quantum states. It's the same. If the vector lambda prime majorizes lambda, then you have the following inequality. So lambda prime minimizes every concave function. So the proof in this direction is trivial. It's just the definition of concavity. That's good. The difficult part is the other direction. If it is true for every function, then you have this. So let's assume that the state doesn't majorize this vector doesn't majorize the other one. Then we have to show that there is at least one function which is strictly concave and for which this is not valid, okay? And we will construct this function. So if this is not true, then there is, by definition, a minimum integer n such that this is violated. This is the definition of majorization is this with the opposite sign here, okay? So if this is not true, there is a minimum n such that you have this. Then let's take the minimum, this n. Let's take the eigenvalue of lambda prime corresponding to this integer n. Let's call it a lambda prime n. Then you just take this function, which is linear, so which is like x in this region, and equal to a constant after this this point, okay? This is lambda prime n, lambda prime n. Then it is easy to show that this violates this inequality. Just do a little bit of calculations. It's just comes, and this is the usual proof that you have. You can find in the literature. So for every concave function, you have this result. And this is indeed a concave function, but it is not strictly concave. This is, for our result, we need to prove this for every strictly concave function. It is not strictly concave because it's linear here. So if you mix 2 points here, you don't get a strict difference. But this is just not a problem because we make it strictly concave. We just add an epsilon correction to it. Just add epsilon x squared. And we send epsilon to 0. So we make it small enough, not exactly to 0. So this function is strictly concave. At some point, it will still violate this inequality. So we have this equivalence relation. This is what we used in the proof. Okay, I think this was also fast, but it's finished. I say that the proof is very simple, and that's the beauty part of it. Okay. Thank you. Okay. So
this is a very nice result because then we have much fewer open questions to worry about. So it clears almost everyone, so every other province. Are there any questions here for the speakers? Yes. So microphone. Yeah, microphone is.
Yeah. So quantum capacity is still open. Are there any other conjectures which would imply the quantum capacity which might be easier to think about?
Well, I don't know, because a powerful conjecture is this entropy photon number inequality. So it is not clear if this directly implies the quantum capacity, I think. But it is very powerful. So maybe with a little bit of work, one could try to, to map this into this. But actually, I'm not sure which one is easier, because all the tricks that we used here just doesn't, they don't apply to this case. It's, they are both very hard problem, I think. So.
Yeah, actually, I have a question. So, could you give us some intuition why this powerful tool you use to prove this major Gaussian channel majorization question cannot be used to prove this photon number conjecture? That means some sort of intuition.
Well, I think the main point here is that all the optimization in all these other cases can be done assuming a pure input state. So the optimal state, we know that it will be pure. This simplifies a lot the proof. In the entropy photon number inequality, you have like a minimization of the output entropy, if you want, with the constraint of a fixed input entropy. So you fix the input entropy, you say what is the minimum output entropy. This is much harder to prove. All the tricks, they don't work.
Do we have any other questions?
So I'm not very familiar with this, but I thought there was another conjecture which states something like, if you have two modes, A and B, and you input them into the beam splitters and call the output C, then the entropy of C is there's some conjecture about that, about maximize. Does that fall under this?
That's exactly the entropy photon number inequality or the entropy power inequality. So if you linearize them, you get.
Oh, is that as strong as the entropy power inequality? The entropy power inequality implies that, right?
Yes. Yes.
So that's a weaker conjecture.
But it depends on what you mean. So if you say what is the minimum output entropy, if you fix the input entropy, this is exactly the conjecture of entropy photon number inequality.
I see.
It's another way of stating it. But maybe you can say that, let's say, the output entropy is like concave, let's say super linear in the input entropy. If you have a beam splitter that mix two states with entropy S1 and S2, the output will be larger than a convex combination of the two, something like this. That's called the linear entropy inequality. And this is a particular case of this, and this has also been shown much before of this, for example. It was already known.
Okay.
But this is weaker than minimum output entropy.
Thank you.
Okay.
Any more questions? So if not, let's thank the speaker again, and we move on to the next one.